All right, so in this task, we're pushing a cart. It's rolling up an incline and back down. The motion detector's at the bottom, and we're collecting data. We're only starting when the cart's already in motion on the way up the incline. And we're looking at these two graphs. Now, the goal of this task is really to figure out how to relate those curves and the equations for those curves to the kinematics equations. I'm not going to really step through these one by one, but I'm going to answer them all just sort of as I go through this explanation. So I went ahead and I already generated the graphs. I got data earlier, and I fit these two functions onto it. Now it's pretty clear why this one is a linear equation, right? This is pretty obviously a line. So I fit a line to this, but for this one, it's a little harder to tell what kind of a curve it is. I'm going to go ahead and fit the one that I know it is, and it should be clear in a minute why I'm choosing this kind of curve. I had it just a minute ago. I just deleted it because I wanted to show you how to do it again. But I'm going to fit a quadratic, which is this type of curve right here, right? Instead of an x, we've got a t value because time is our independent variable. Let's fit that. And it will become pretty clear in just a second why I chose this kind of function. So as a starting point, let's look at the kinematics equations and try to relate them to our velocity versus time graph right here. So, that's position. We want to look at velocity versus time. We'll come back to position versus time in a minute. So for our velocity versus time graph, let's just think about how this relates to these. Well, this is a linear equation. Velocity, as it's linear related to time. And if we look at our kinematics equations, well, this one right here is exactly the same form as this. It's also a linear equation. So if we think about what these terms actually mean, right, this is the initial velocity, this is acceleration times time. These are both constant, right? Only time is changing as the cart moves, and the final velocity is also changing as the cart moves. So if we think about what these represent, this here, this is essentially our y-intercept, this b value. So we can actually interpret our initial velocity, and I can't do subscripts, so it's going to look a little ugly. Our initial velocity here is going to be equal to this, 0.7263. Right? That is the y-intercept of this graph. And it does have units, so I should write them down. Meters per second. Boom. Now the slope of this graph, this value right here, is the acceleration value, right? Because that's the coefficient that's being multiplied by time. So our acceleration is going to be equal to, oh come on. Our acceleration is going to be equal to this, negative 0.8592 in meters per second squared, or just meters per second. That's the slope. It makes sense that this is negative, right? Because our initial velocity is positive, but the cart is slowing down to begin with. So different signs indicate that it's slowing down. So now let's go ahead and try to do the same thing, but for our position versus time graph. Now here, if we look at the position versus time graph, we do not have a linear equation. We actually have a quadratic equation. And in this position versus time graph, we've got three different coefficients. One in the term with t squared, one in the term just with t, and another one by itself. Now, if we look at the kinematics equations, well, that is exactly this same format, just with the terms in a different order. So if we think about this term first, right, this is our initial position. This is where the object starts at a time of 0. Which is sort of right here on our graph. That's essentially the y-intercept of this graph. It's the starting position. Well, that starting position, we know it, right? We can just come in here, and it's just going to be this c value right here, 0.4897 meters. Right, so that's the c coefficient. Ooh, it completed that for me. All right, now let's look at the next term. All right, this next term only has one t in it, so the coefficient out in front of that is the initial velocity. Well, that's our b value right here. Right, here's our b value. So the initial velocity is going to be this right here, 0.7169 meters per second is the b coefficient. All right. Now last, we've got this term. Now this is a little bit weird because we've got a 1/2 here, but this whole thing is constant, right? 1/2 times the acceleration. That should be equal to this big A, capital A, coefficient out here in front of the t squared. In other words, if I were to type it out, I could write something like that. Capital A value is equal to 1/2 times the acceleration. So if I solve for the acceleration, it's basically, whoops, going to be equal to 2 times that capital A. Right? And if I do that, right, here's the A value, it's negative 0.4262, negative 0.4262, and if I multiply this by 2, I get negative 0.8524. Negative 0.8524. And that's going to be in meters per second squared, or meters per second per second. And I can just go ahead and put that, oops, up here. Perfect. And that is the, I guess it's 2 times the capital A coefficient. Gives us our acceleration. Cool. So now we can see how the motion graphs actually relate directly to the kinematics equations. And if we look at our velocity versus time one, we compare it to the position versus time one, we're getting pretty similar values, right? Here's the acceleration we got from the slope of the velocity versus time graph. Here's the acceleration we got by analyzing the position versus time graph, right? Off by a little bit, but almost exactly the same. Similarly, oh, there's an error. That should be seconds, not 2. The initial velocity, we got this using the position versus time graph, and we got this using the velocity versus time graph. All right, cool, cool.